Hi, I'm Robin Clancy from the University of Washington, and I'm here to give my EGU 2021 talk on the drivers of the spatial pattern of the Arctic sea ice response to Arctic cyclones. If you're watching this on YouTube, there should be some timestamps in the description if you want to go ahead and skip to your favorite part of the talk. Okay, so what are Arctic cyclones? To put it simply, they're like mid-latitude cyclones. They're closed contour, low pressure systems, but they occur in the Arctic. So to look at their structure, I'm going to start with a paper by Eizawa and Tanaka from 2016. And in their paper, they put forward this figure at the bottom of this slide, which is an axisymmetric paradigm for Arctic cyclone structures. So there'll be some familiar features for you if you're familiar with mid-latitude cyclones, like a low-pressure center and cyclonic winds around this low-pressure center. There's updrafts at the center and then downdrafts further at range. And then maybe some features which are less familiar if you're looking at mid-latitude cyclones, like a cold core, longer lifetimes, and a larger spatial diameter. So Eizawa and Tanaka came to this structure after analyzing a couple of case studies. And so we're going to see, if we look at a larger number of cyclones and statistically analyze their structure, does this axisymmetric structure really hold up in reality? What we're also going to look at is how these cyclones affect Arctic sea ice. So to start with, I'm going to look at this Great Arctic Cyclone of August 2012. And one of the reasons it's called the Great Arctic Cyclone is because it had such a large effect on Arctic sea ice. In fact, September 2012 was the lowest sea ice extent ever on record, and one of the contributing factors was this cyclone. So I'm going to watch this film from NASA that shows the influence of this cyclone on sea ice. If you look north of Alaska, you'll see there's quite a lot of sea ice, and it very quickly disappears as this big swirly cyclone comes in. I'll play it again because that happens, like I said, quite quickly. Just look north of Alaska, there's a lot of sea ice, and then these swirly red arrows, that's the cyclone, and then the sea ice over a couple of days very quickly disappears. So this event got a lot of people looking at how cyclones affect sea ice, and the big question everyone was trying to answer is, do cyclones cause an increase or decrease in sea ice? And alongside this Great Arctic Cyclone case study, other people had other case studies in different seasons. This paper looks at case studies in winter and found that cyclones cause a decrease in sea ice in winter. And some other people looked at it more statistically. This paper found that regions had reduced sea ice in seasons where there were more cyclones over that region. But it's not so simple. Another statistical study here looks at the correlations between either the count of Arctic cyclones or the intensity of Arctic cyclones in a given season and the sea ice extent in that season. And depending on how the cyclones were tracked and the reanalysis data product used, you get very different answers for what this correlation should be. In fact, completely different signs. Then there are papers that have found increases in Arctic sea ice associated with cyclones. This paper found that locations had increased gain of sea ice when they were within the sphere of influence of an Arctic cyclone, so within the radius of an Arctic cyclone. And this occurred in all seasons. And this paper found something similar in summer, particularly focusing on the marginal ice zone, which has been shown to be a key area for where cyclones influence sea ice. They found that summer cyclones reduce the amount of melt going on, so lead to more sea ice. So on the left, we've got some suggesting decreases in sea ice. On the right, some suggesting increase in sea ice as a result of cyclones. This is very much not a settled question, but one thing several of these studies have in common is the marginal ice zone being a key area where cyclones have an influence. There's one more paper I want to discuss, and it's this Kriegsmann and Brummer paper from 2014. And they addressed this problem in a slightly different way. They didn't just ask, do cyclones cause an increase or decrease in sea ice, but they also asked, what pattern does this occur in? So I'm going to start with this figure in the top right, and each dot in this figure represents a different cyclone in their data set. And you can see they're all within the central Arctic Ocean. So what they did was they regridded the changes in sea ice concentration around each cyclone center onto a new grid, which is this XY axis I've circled in the top right, and the two red lines I've kind of drawn on in the bottom left. So when they regrid the change in ice concentration such that it's centered on each cyclone center, and then composite this all together, they get the average spatial pattern of the sea ice response to cyclones. And you can see that both for where they simulate this in a sea ice model and where they just take it from satellite sea ice concentration output, you get reduced sea ice concentrations near the center of a cyclone. So there's some reasons why we think that this might not be the full story, and it's based on the methods that they use. The first is they only use 3 years of data, and we found that large data sets and big sample sizes are really useful for answering this question and getting above the signal to noise issue for how cyclones affect sea ice. The second is that they focus on the central Arctic only, and I mentioned in the previous slide, the marginal ice zone is really a key area where you get most of the response to cyclones for sea ice. And the third is this somewhat arbitrary reference frame, this XY that's in the top right. And you can see that in some parts of the Arctic, y will be pointing north, in some parts of the Arctic, y will be pointing south. And this acts to kind of smear out some interesting spatial patterns that we'll get to later. So to summarize, there's some open questions that we'll address in this talk. The first is, what is the structure of Arctic cyclones? And particularly, is it axisymmetric and does it match this Aizawa and Tanaka model? The second is, how does the sea ice respond to Arctic cyclones? Does it increase, does it decrease, or is there some spatial pattern? And if there is a spatial pattern, does it match this Kriegsmann and Böhmer pattern? And the third question kind of relates question 1 to question 2. It asks, how does the structure of Arctic cyclones result in the sea ice response to these cyclones? So there's some possible mechanisms we want to get at, and we want to see which of these dominate. And this diagram I've drawn in the bottom right shows some of these mechanisms. The white is the sea ice, and these green arrows are the surface winds, causing the sea ice to be transported and dynamically advected into kind of new spatial patterns. The red and blue above the sea ice are the surface energy fluxes. So anomalies in these could cause thermodynamic changes to the sea ice, increases in growth or melt of sea ice. And likewise, you can get this thermodynamic effect underneath the sea ice at the base, caused by the ocean. So you've got dynamic advection by the surface winds, thermodynamics above and below the sea ice being 3 possible mechanisms by which the sea ice could respond to cyclones. So the data sets we'll be using, the first and most important, I guess, is the Arctic cyclone tracks we take from Spreng et al. 2017. And these are locations and intensities that we use from these cyclone tracks. So I've plotted the locations in this bottom left figure, and you can see that in each season, you've got a fairly high chance of being near to an Arctic cyclone. You can see there's a different spatial pattern though in different seasons. In summer, you get a lot of Arctic cyclones near the center of the Arctic, but in other seasons, you tend to get more Arctic cyclones near the North Atlantic. So we don't use every cyclone in the Spreng et al. 2017 data set, and that's because there's a lot of very weak cyclones in there, which we'd expect to not have much effect at all on Arctic sea ice. So instead, we just select the 25% strongest cyclones in each season based on an amplitude threshold, which is what we show here in the bottom right. And you can see this threshold is higher for autumn and winter than it is for summer because there's stronger cyclones in autumn and winter. And so the cyclones remaining after we apply this amplitude threshold, we can show the count of those in each season and each year, and that's in the top right figure here on this slide. And you can see that we still get a very large sample size to work with for each season. So we combine these cyclone tracks with ERA5 reanalysis to look at the atmospheric structure of these cyclones. We use NASA Goddard bootstrap satellite sea ice concentrations to look at how the sea ice responds to these cyclones and what pattern we get. And then we use size5, a sea ice model, which we force with another reanalysis dataset, JOA55. And that helps us understand the mechanisms by which the sea ice was responding to the cyclones. And so all of these datasets span from 1985 to 2016. So that gives us 32 years. Now, there's one primary method that we use for most of our analyses. So I'll try and explain it here on this slide, and hopefully it's clear. So we start with anomalies of some field on a lat long grid. So this could be sea ice concentration anomalies. I think that's what we have here in this example on the left. Or it could be ERA5 reanalysis anomalies. And on this example on the left, we've also got this red star, and that represents a hypothetical Arctic cyclone center location. So what we want to do is regrid these anomalies on the left onto a cyclone-centered grid. So you can see in the middle panel, the red star is now in the center of the grid, and now the anomalies are regridded onto this grid based on their distance from 0 to 1,500 kilometers away from the cyclone, and their direction away from the cyclone from north going all the way around east, south, west. And so to see what this looks like, you can compare the far left panel with the far right panel. You can see how the cyclone is now in the center, that red star, and the pattern of anomalies has been rotated and projected onto this new grid. And I've also projected the land outline just to show that there's no real distortion going on appreciably. It kind of faithfully regrids on the right shapes and the right patterns. So this is just for one example anomaly field, but we do this for every cyclone center we have in our tracks. So thousands of examples for each season. And we composite these to then get the average response of a given field to Arctic cyclones. So this is quite conceptual at this point. Let's see what it looks like in practice. So here we perform this regridding and compositing upon ERA5 reanalysis anomalies. And in the top row, we have anomalies of sea level pressure, that's shaded, and surface winds, that's the arrows. And so what you can see is in each season, you get a low pressure anomaly at the center and cyclonic winds around that low pressure anomaly. So this is reassuring. This is what we expect from cyclones, and so good news. It seems to be working. And it's fairly axis symmetric. So far we're following the Ezawa and Tanaka axis symmetric model. But the first sign that this axis symmetric model might not capture everything which is involved in Arctic cyclones happens when we look at the vertical motion on the next row. So here the pink shading is an upward vertical motion. It's negative because it's a pressure velocity. And you can see in the center and in the cyclones, yes, you get this uplift at the center. But you also get a tail of vertical motion upwards towards the southeast in each season. And so we interpret this as frontal uplift, which isn't in the Ezawa and Tanaka model. And so this doesn't necessarily say that you have frontal uplift associated with every Arctic cyclone, but it definitely occurs with some based on our definitions of what an Arctic cyclone is. So given we have these horizontal and vertical motions associated with cyclones, we're going to get advection of temperature and moisture occurring. And that's going to create some patterns of temperature and moisture fields associated with cyclones. So you can see on this figure, I've kept two green arrows on one of the figures to kind of show the horizontal directions of the surface winds, kind of north to the east of cyclones and south to the west of cyclones. And these advect temperature to form a temperature dipole in each season. So warm air comes up from the south to the east of cyclones, and cold air comes down from the north to the west of cyclones. And this pattern we've shown here for the 850 hectopascal level, but it extends throughout the troposphere. And so associated with this warm air, you kind of get a lot of moisture being advected too from the south. And that's what we show in the second row, our total column water. And the air being advected down south from the cold air up north is much drier. And so you get this kind of east-west dipole of both temperature and moisture associated with cyclones. And this is now diverging quite a lot from this Aizawa and Tanaka model, which is axisymmetric. So given that we get this temperature and moisture dipole, and given that we have vertical motion anomalies, we'd expect the cloud cover to have some anomalies as well. So this third row is our total cloud cover pattern that we get in each season, and you can see it's slightly different in each season, which is somewhat interesting. We get spiraliform clouds in summer, but comet cloud shapes in the other seasons. But in each season, you get this kind of large anomaly in total cloud cover near the center of the cyclone. And associated with this, you also get snowfall anomalies. That's what I have plotted in the final row at the bottom. And it's about 1 centimeter per day increase in snow depth, resulting in each season outside summer, which is slightly less, near the cyclone center. So, given we have all these influences on the cyclone, on the atmosphere caused by the cyclone, we've got changes in temperature, water vapor, cloud cover. We'd expect to get some influence on the surface energy balance. And so this is what I show in this slide. And I think I'll start by just running through what each row shows. So in each case, positive values are downward fluxes. So they're fluxes into the sea ice or the ocean surface. So the top row is our net long wave anomaly associated with cyclones. The next row is our net short wave. Then we have the surface latent heat flux, the surface sensible heat flux, and then we have the total surface energy anomaly, which is the sum of all the other ones plotted in the final row, row E. So I'll start at the top, kind of running through this, and it should be fairly easy to interpret that the net long wave anomaly matches our temperature anomalies and our cloud cover anomalies. So warm, moist air emits more long wave radiation, and that's reflected here. Somewhat the mirror pattern, the opposite pattern, is seen in the net short wave, as clouds are now obviously blocking light from reaching the surface. But there's more of a seasonal cycle to the net short wave at the surface, as during winter it's polar night in the Arctic, so you aren't able to get any anomalies. I won't go too much into breaking down the surface latent heat flux and surface sensible heat flux patterns, but you can see they correspond quite closely to the east-west pattern of the temperature and moisture dipoles, and so you get increased energy going into the ice surface to the east and decrease to the west, and all of these kind of sum up to, in the total, give this dipole of more energy going to the surface to the east of cyclones and reduced energy to the west of cyclones. So given that we have these spatial patterns of surface energy flux anomalies, and we have anomalies in the surface winds caused by cyclones, we'd expect some response of the sea ice surface. And we can look into that here in both satellite sea ice concentration data and concentration data from our CICE5 sea ice model. So I'll start with the satellite sea ice concentration data. That's our top row here. And the exact quantity plotted is the anomaly in sea ice concentration change from 5 days before a cyclone passes over a point to 5 days after a cyclone passes over a point. That's a little complicated, so I'll just say that all you really need to understand is where you see this greeny blue color, that means you're gaining sea ice faster than normal, and where you see a brown color, that means you're losing sea ice faster than you would normally. And so we can see in each season we get gain of sea ice to the west of cyclones, and we lose sea ice faster than normal to the east of cyclones. And this pattern we get not just from the satellite sea ice concentration data, but we also get a very comparable pattern in the row below from CICE5. And so this gives us some faith that CICE is able to recreate the pattern correctly, and therefore the physics is probably relatively accurately represented for how the sea ice should be responding to cyclones. And if we have some faith in what CICE5 is doing, we can pull out extra information that we wouldn't be able to get from just observations. For example, we can take the effects of cyclones on sea ice thickness from CICE5, and we get a very similar pattern to what we get for sea ice concentration. You get gain of sea ice thickness as well to the west of cyclones and loss to the east of cyclones. So one thing we wanted to do was to determine where regionally this east versus west pattern of sea ice concentration gain and loss occurs in the Arctic. And to do that, we've got these maps here on the right where we plot some measure of the strength of the east-west pattern that you see in the top left. So where you see these dark blue colors, that means that you're gaining sea ice when that location is to the west of cyclones, and you're losing sea ice when that location is to the east of cyclones. And you can see this pattern is prevalent in each season, but largely constrained to the region between this red and purple line. And those red and purple lines mark the 15 and 80% sea ice concentration contours in the climatology. So that's a measure of where the marginal ice zone is kind of roughly located. So what this says is fairly consistently within the marginal ice zone, you get this east versus west dipole of gain of sea ice to the west of cyclones and loss of sea ice to the east of cyclones. So this figure is from satellite sea ice concentration data, and we have a similar figure for size 5 sea ice concentration data. If I flick between them, you'll see that there's fairly good agreement in both the locations, the strength, and the seasonal changes in these patterns. So all of this, again, gives us quite good faith that the size 5 model must be getting some of the physics accurately represented in how sea ice responds to cyclones. And so we're going to break down why the sea ice responds in this way using size 5. So the first way we can break this down is splitting the sea ice response into its dynamic changes, that's changes due to advection by winds, and thermodynamic changes, so that's changes in growth and melt of sea ice. And so if we start with the first row here, that's the dynamic changes of the sea ice concentration. And this should be familiar by now. You see gain of sea ice due to dynamic processes to the west of cyclones and loss of sea ice due to these processes to the east of cyclones. And we've done quite a bit of work that I won't go into a lot of detail here in trying to understand why this happens. And it seems to be very tied to the south to north gradient of sea ice concentration. So as you go further north, you tend to get higher sea ice concentrations. And so when you apply a cyclonic velocity field to this gradient, you're going to get divergence to the east of cyclones and convergence to the west. So you're essentially shifting along the gradient, either north or south, and that causes this divergence. I can talk about that more if anyone has any questions. So moving on to the thermodynamic change, the first thing I want to point out is that the absolute magnitude of the thermodynamic sea ice concentration change is about equal to the dynamic change. Both are definitely important in determining how the sea ice responds to cyclones. The one thing I would say though is there's less of this east-west pattern. You could argue there's some east-west pattern, particularly in summer and fall, but it's certainly less consistent. And so my takeaway from this is that thermodynamics are also important in determining how sea ice concentration changes in response to cyclones, but that they drive less of this east versus west pattern that we've been talking about specifically. If we look at the sea ice thickness change due to dynamics, that's the third row, you can again see this east versus west pattern comes out very strongly. And when we look at the thermodynamic component of that, which I haven't plotted, it's very close to zero. These anomalies are fairly insignificant. So the dynamics are more important for the thickness than they are for the concentration, and the thermodynamics barely matter for the thickness effect. So I want to break down the thermodynamic processes a little further because there's a lot of mechanisms by which the ice can change thermodynamically. So the first thing I want to look at is anomalies in the melt of ice at the top surface. So that's this top row that I've got here, row A. And you can see that only in summer do you get anomalies in ice top melt. And this makes sense as this is the only season where the ice surface is kind of close to its melting and freezing point. And so this is the only time when the surface energy flux anomalies that we had previously can really work on the ice surface and cause it to change phase. And so this is one of the reasons why the thermodynamics drive an east-west pattern in summer, at least. The next row is the basal melt, and this is really determined, we think, by upwelling and mixing of warm waters at the surface by the surface winds. And one of the reasons we think that is because the patterns that we see in row B, particularly in summer, mirror the patterns of surface wind speed anomalies. So higher wind speeds means more turbulence in the upper ocean, which means warm water is able to melt the lower surface of the ice. And that's why we get these patterns. But these patterns don't have this east versus west gradient, so they're not really driving the east versus west difference in how sea ice responds. The next two rows we have congelation and fragile ice growth. And the difference between these is congelation ice growth involves the thickening or thinning of, thickening of already existing sea ice in the size 5 model, whereas fragile ice growth is the growth of new sea ice from open water. And the first thing I'll point out is that in neither of these do you get much of an anomaly in summer, and this makes sense. There isn't much ice growth going on in summer, it's almost all melt. And I'll also point out that you do get some east versus west gradient going on, particularly in autumn for the congelation growth. So that's the reason why in autumn we're seeing some of this east versus west gradient in the sea ice response in the thermodynamic term. I won't get into the reasons behind a lot of these patterns. I've thought about them some and would be very happy to discuss them more, but yeah, I'll just skip forward for now. So, my conclusions. The first is looking at what is the structure of Arctic cyclones, and was it axisymmetric? Was it like this Aizawa and Tanaka model? And what we found was that although some features are fairly axisymmetric, such as the low pressure in the center of the cyclones and the winds around it, a lot of features are decidedly not axisymmetric, such as the temperature fields. We don't find these systems to be cold core so much as having a warm cold dipole in them. And the clouds themselves and the moisture content also are not axisymmetric. So we generally, I think it's safe to say we can reject a lot of this Aizawa and Tanaka axisymmetric structure in more of favor of an east versus west dipole for a lot of the structure of Arctic cyclones. Okay, next question we wanted to address, how does the sea ice respond to Arctic cyclones? The key thing is that we've got this east versus west pattern of how the sea ice responds. You gain sea ice anomaly to the west of cyclones, and you lose sea ice anomaly to the east, anomalously to the east of cyclones. And this pattern occurs throughout the marginal ice zone. And so this is kind of interesting to compare to a lot of other work, which is focused more on do you get a gain or a loss of sea ice. We find that you get both. It depends on where you are relative to the cyclone, and this might help explain why we've had such a hard time pinning down the answer to if you get increases or decreases in sea ice, as you've got two competing effects which could win out over each other on any given day. Okay, and the third question is trying to relate the structure of cyclones to why the sea ice responds in such a certain way. And what really dominates this east versus west pattern is the dynamics. So this is the surface winds infecting the sea ice into this pattern, although there is some influence of thermodynamics in some seasons as well. And the thermodynamics is still very important in determining kind of the overall influence. They just don't have this clear east-west pattern as much. What we do find from the thermodynamics is that in summer, at least, the top melt has the east-west pattern, and in all seasons you get this influence of the ocean being upwelled and mixed and causing increased bottom melt with cyclone activity. And then there's some influence again on the congelation and fossil ice growth. It's a little more complicated maybe to interpret, and so I'll happily talk about that in a bit more detail with anyone who wants to hear. But overall, these are my conclusions. Thanks for listening, and I'm happy to answer any questions however anyone wants to get in touch with me. Thanks.